Lecture 6.4, Day 1, Separable Differential Equations. This is the Jefferson Memorial in Washington, D.C., not quite as well known as the Lincoln Memorial. In the Jefferson Memorial, Thomas Jefferson's statue is standing. A separable differential equation can be expressed as the product of a function of x and a function of y, as in dy dx equals g of x times h of y, where h of y is not equal to 0. Example, dy dx equals 2xy squared. We can multiply both sides by dx and divide both sides by y squared to separate the variables. Assume that y squared is never 0. So we get dy over y squared equals 2x dx. We rewrite the left side as y to the negative 2 dy equals 2x dx. Now we integrate both sides. The left side becomes negative y to negative 1 plus a constant. The right side becomes x squared plus another constant. We can combine the two constants of integration into one constant, since it's an arbitrary constant anyway. Now we solve for y. And our answer is y equals negative 1 over x squared plus c. Notice that the constant of integration is not at the end. In this case, it's in the denominator. Here is another example. dy dx equals 2x times the quantity 1 plus y squared times e to the x squared. It is a separable differential equation because it is a product of x terms and y terms. We divide by the y term and get 1 over 1 plus y squared dy equals 2x e to the x squared dx. Then we integrate both sides. On the right side, we'll let u equal x squared, so du equals 2x dx, so we can integrate by substitution. On the left side, there's a formula we recognize. So when we integrate both sides, we get inverse tangent y plus constant 1 equals e to the u plus constant 2. Now we substitute back in the value for u, which is x squared. Combine the constants. We now have an implicit function of x. That is, it could be interpreted as a function of x, but it's not solved for y yet. We can find y as an explicit function of x by taking the tangent of both sides to undo inverse tangent. Tangent and inverse tangent cancel each other out, and we get y equals the tangent of the quantity e to the x squared plus c. Notice that we cannot factor out the constant c because the distributive property does not work with tangent. To do the same problem on the TI-89, press F3 Calculus, C, D-Solve to open the differential equation solver. Now enter the differential equation as shown. We have d-solve y prime equals 2x times 1 plus y to the second times e to the x to the second, comma x, comma y. We use second equal to get the prime symbol. Use the multiplication symbol here. Implied multiplication after a variable does not work. X is the independent variable, and y is the dependent variable. Now press enter to get our answer. We get inverse tangent y equals e to the x squared plus a constant. In this case, the calculator does not explicitly solve for y, so we can try using the solve function. Use copy and paste to insert the expression into the solve command and solve for y. We get y equals tangent e to the x squared plus a constant, and this solution includes restrictions on the domain. We highlight the solution and scroll right to see the rest of the answer. We see that one of the restrictions is e to the x squared plus the constant must be less than or equal to pi over 2. And the other restriction is that e to the x squared plus a constant must be greater than or equal to negative pi over 2. These restrictions are why the differential equation solver wouldn't give us an explicit solution in the first place.